Hey, here's a demo and some background on homework 6B. So I've already finished my example washer code. I'm going to run task 3.2, the washer driver. So that'll pop open three different panes here. The rightmost pane is the LED and keyboard. Then the left two panes are the washer driver, where the code that actually kind of controls everything and calls your function is at. It also opened up simulate.s. So this just imports all of the files. This is really what's being run, but it's just a way of combining together all of the separate files for the purpose of the simulator. So I'm going to go ahead and hit play. The mode is shown over on the leftmost digit. The leftmost button, S1, allows us to advance through the modes. The rightmost digit will be the start button. The digit just to the left of center in the 10,000s place will represent which of our outputs are being activated. And the digit all the way to the right will be controlled by your spinner, and we'll kind of show the progress through an individual wash cycle. So I'm going to do one run through mode 0. So it's going through the first phase and then the second phase. Did 2 cycles in the second phase. Now it's going through the third phase. Single output is on. And finally, it's done. Some of the cycles will take longer than others. Some of them, the spinner will move faster than others. Okay. So once we've done that, we can use a task to build the firmware. So I want to talk just a little bit about what's going on with the firmware and how we're using the UPduino. So I'm going to switch over to web page here. So I'm going to connect to my UPduino, and I'm going to go ahead and upload the Pico RISC-V 32-bit IMC implementation. And I want to give a little bit of background about what's going on there. So our UPduino has a couple of different memories. I'm on the upduino.readthedocs.io page, and it describes the different parts that are on the UPduino board. The most important one is probably the Lattice Ultra Plus ICE 40. This is the actual FPGA part. Within that FPGA, it has a couple of different types of memory. So it has a 1 megabit SP RAM and 120 kilobit DP RAM. We'll come back to that in just a second. It also has a 4 megabyte SPI flash chip. So just kind of for some background, here's kind of what the schematic of the UPduino looks like. The part highlighted there in red is the actual FPGA, and this part sitting next to it is the flash memory. So when we send code over to our UPduino, we're actually putting it inside of this flash memory. When the entire system here powers on, it will then pull in that bit stream from the flash memory. Okay, so let's talk a little bit about how this fits in with our actual computer memory thing here. So we talked a little bit in class about how the computer will use its RAM memory, and we kind of described this idea of memory being divided up into these different regions that serve the different needs of the program as it's running. But one of them contains the program itself, the text part of the program. And then we've also got this stack thing and this heap thing where we store data as the program is running. And then there are oftentimes other places to store data for initialized data and uninitialized data. So we split the entire RAM into different regions to serve different purposes that we need. So one of the ones we're spending a lot of time on is trying to understand the stack and use it correctly. And that's important to be able to break programs into smaller modules. We're not dwelling too much on the heap in this particular class, but it's also a really important concept for dynamic memory when you need to create things on the fly, which is very, very common in modern programs. Okay, so we looked at the overall CPU diagram, and the particular structure we're looking at here is called the Harvard architecture. It splits the memory into kind of two different pieces, the data memory and the instruction memory, instead of having everything in one unified memory like in that previous diagram. But we can kind of think of that, the bulk of that memory structure is going in the data memory over there. It's only the bottommost piece of it, the text, that's over in the instruction memory on the left. So I wanted to look at this with respect to the actual UPduino chip and the FPGA on it. So we have this 1 megabit SP RAM, and it is inside of the FPGA chip itself. And just further detail, it's 1 megabit of single ported RAM. That's what the SP is, single ported. So we can read to it or write from it. We can basically provide one address and get data out from that address or write data to that address, single port. That entire memory thing that we've been talking about, this entire view of RAM, is essentially that single ported RAM. That is where it is allocated within the FPGA. Okay. We also have that other chip, the 4 megabit SPI flash chip that sits right next to the FPGA. So we put two things in that. We put the hardware configuration file for our RISC-V processor. So when we go through and use the FPGA loader to upload the Pico RISC-V 32 onto our UPduino, it's actually taking that configuration file and it's putting it inside of this part. Later on, then we also upload a second file that represents the code for our program, the stuff to go in the .text segment mainly, and it also puts it inside of that part. And we can do these independently. They kind of go in different places within that big 4 megabit SPI flash memory. Then when the entire UPduino system powers up, that hardware configuration file is transferred from that flash memory into the FPGA, and it configures the actual routes around within the FPGA and basically sets it up to behave like a computer. A little bit of time after that, once the FPGA is behaving like a RISC-V processor, it runs some code that will then copy that text segment over and put it into the FPGA's RAM. So these two different files that we're creating, both of them end up in the flash memory, and they are pulled into the different parts of the UPduino at different times. The bit stream for the processor, the overall blueprint for our computer, happens when the UPduino first starts up. A little bit of time after that, the code that we want is pulled into the UPduino's SP RAM, and we begin executing out of it. A quick demo of the hardware itself. So I'm going to go ahead and build my updated firmware, and I'm going to switch over and make sure it's uploaded to my UPduino. Okay, and now I'm going to take a look at the UPduino over here. So just like before, the leftmost button controls our modes. I'm going to do mode 1. Rightmost button is going to start a wash cycle. I have made sure to update my delay so it's appropriate for the UPduino. If I left it set up for the simulator, this would probably be so quick I'd barely notice anything. So I'm going to go ahead and start a cycle. So mode 1, it does kind of a slow cycle first, and then it does a little bit faster cycle, and then it's done.